So if we were in class together, there would be a couple of questions that I would do, a couple of things that I would prove at the start of our class time. I would work through those with you and we'd model how to write things up. That's the reason I've picked these two questions. So let's take a look at what I'm asking us to prove. I'm asking us to prove that for any angle BAC, and we remember that an angle is a union of two non-opposite rays. So angle BAC is the union of AB and AC. There exists a unique ray AD, and if we write out the word ray, we don't need the symbol. But if we don't write out the word ray, we do need the symbol. And in either case, A and D are italicized, as are B and A and C when you go to write this up. So we want to prove that there exists a unique ray AD such that AD bisects angle BAC. So we're going to start with the only thing that they've given us, and that is to suppose that we have an angle BAC. So what we want to show is that there is a ray, that ray is unique, and that ray bisects angle BAC. So how do we get to that? Well, we know that the measure of angle BAC is some real number R, where 0 is less than or equal to R. No, we know that 0 is less than R, is less than 180. Not much of an angle otherwise. We could say less than or equal to. We could deal with the trivial case. Clearly, if R is 0, then AB and AC are the same, and the angle bisector AD is the ray AB, is the ray AC. So I'm going to deal with the non-trivial case where R is positive and less than 180. Consider R over 2, which is also a real number, because 0 is less than R over 2 is less than 90. By the protractor postulate, there exists a unique ray on the B side of line AC such that the measure of angle CAD, there exists a unique ray AD on the B side of AC such that the measure of angle CAD is R over 2. So we come up R over 2 and we have this ray right there. So now all we have to do is show that that ray is a bisector. By the protractor postulate, the measure of angle BAD is R minus R over 2, and that's R over 2. So AD bisects angle BAC. We have already got the uniqueness by the protractor postulate, so we don't have to finish the argument with uniqueness. Uniqueness comes from the protractor postulate. So this is something that we do on occasion. We have a geometric figure with a property that is a real number. Then we go play with real numbers, and then we say, okay, that real number corresponds to a geometric figure. That figure happens to be this ray, and that ray does the thing we want it to do. Okay, so the second question I wanted to consider in our time. If L is perpendicular to M, then L and M contain rays that make four different right angles. Four different right angles. What's that all about? Isn't that the whole deal with perpendicular lines? Well, by definition, perpendicular lines create one right angle. The question then becomes, where are the other three? Like, where do the other three come from? So let's consider that. We can do this. And this proof is one that I walk through with students because I want them to know how to set up the picture. So this is what we know. Suppose L and M are lines with L perpendicular to M. Well, what does that mean? That means that L and M come together and form a right angle. Well, we've got to give that angle a name, so let's do that. Let L intersect M be the point A, and let B be on L and C be on M, such that angle BAC is right. BC. So we have to give the reader a way to see what the right angle is. We can't just say, draw this picture, clearly there's a right angle. We can't say, refer to the figure, because we want to build the proof without the figure necessary, without the figure being necessary. So where are the other three right angles? Well, we've got to build other points in the picture. So let's build this point. How do we build this point? Choose a point D on line M with A between C and D, and a point E on line L with A between B and E. So now our job is to argue that this is a right angle, this is a right angle, this is a right angle, and we can do that. So by the linear pair theorem, the measure of angle BAD plus the measure of angle BAC equals 180, and the measure of angle, let's get this, EAC, which, as we all know from Nemo, is the East Australian Current. Those sum to 180. So the measure of angle BAD is 90, and the measure of angle EAC is 90, and thus angle BAD and angle EAC are right angles. So then we've got to get the one more. We've got to get angle EAD, and we can do that also by the linear pair theorem. The measure of angle EAD plus the measure of angle EAC is 180. So the measure of angle EAD is 90 and EAD is right. Therefore, L and M form 4 right angles. Done. Can I highlight a couple of things for us? Measures of angles are numbers. Measures of angles can add. Angles themselves are right, but their measures are numbers. This is a thing that sometimes geometry students get sloppy about, and they'll say, oh, so angle EAD plus angle EAC is, well, we can't add angles, we can add the measures of angles, because we add numbers, we don't add figures. Okay, that's a thing to keep in mind. Couple of good examples for you. Hope things are well.